Okay, guys. So, you wanna discuss something here regarding? Guys, you wanna discuss here something? No questions? Because I saw that you were talking about the assignments. Is that true? Is there something that? All right. Okay. I guess you want. It depends. I will not give you a solution, let's say. All right. Okay, guys. Now we continue. We were talking about closed sets, open sets, etc., etc., etc. You know that. And we also were looking at some basic properties. Okay, closed sets and open sets. Okay. For instance, the union of closed sets or countable union of closed sets is not necessarily closed, or the intersection of open sets is not necessarily open. Okay, so we've seen this before, right? Okay. Now, maybe you remember, like last week, we introduced a concept which was based on sigma-additivity generated by a certain family guy. Okay, so there exists always a smaller sigma-algebra that contains all elements of the family. Okay, so let me just repeat that. So that was actually, maybe this example. So suppose that F is a family of sets over omega. Okay. Sorry if you can't read this. I can't read it myself. Okay. I have to try it again. Okay. I tried again. All right. So. Okay. So. Suppose the following. So we have here an example. Okay. And maybe you remember that concept. I'm not sure if you remember that. So that was from last week. Okay. So suppose that F is a family, okay, basically a family of sets, okay, over omega. You know what this family is? A family is actually a subset of a power set, okay, subset of a power set. Remember, it's not necessarily a sigma-algebra, so it's not necessarily close under complementation or close under countable unions, okay, so not necessarily a sigma-algebra, but then there exists. Okay, so then there exists the smallest sigma-algebra, okay, a smallest sigma-algebra, okay, and I call it sigma of F, okay, and this is a sigma-algebra generated by the family F. So namely, the sigma-algebra generated by F, okay, that has all that contains all elements here from F, okay, so that contains all elements of F. Okay, so that was, I think, I'm not sure if you remember this, but that was theorem, I'll give you a number. I think that was theorem 2.21, okay? So that was theorem 2.21, okay? All right, so I hope you remember that. So that can be also applied to open intervals, okay? So this is what I do. So just I want to recall that. And I will continue here. So this will be a mark, okay? Forming mark. And what I do is I put the set of open intervals on R. I put that into a set, and this will be also a family, okay? So the set of open intervals, the set of open intervals on R, namely and I call this also capital F, okay? So that is the set of all open intervals. This is actually what it is about, where you can see that, okay? So where A and B are real numbers, okay? And here in this case, I mean, if you, let's say for instance, the upper bound or the lower bound is plus or minus infinity, then you also have an open set, but this is not what I would like to actually to talk here, okay? But that should be enough, okay? This actually, I mean, we showed this, that this is not a sigma algebra, okay? So this is not a sigma algebra, okay? Why? Because among others, because it's not closed under complementation, okay? So the complement of a certain interval, okay? So for instance, we have the interval from 0 to 1, okay, which is an open interval, and the complement of that is not in there, okay? So that's one reason actually. And the set is also not closed under countable unions or countable intersections, but anyway, so this is not a sigma algebra, okay? So because it is not closed under complementation among others, okay? Again, complementation, okay, among others. Okay. It is also not close to the countable unions and countable intersections either, okay? This is just an implication, okay? All right, so basically, I mean, of course, it's close in under here. You could just say the countable union of open intervals is open. So, but since it's not close under complementation, it's not close under countable intersections, you guys. Okay, but okay, so that's one reason. Okay, but the family generated by that. Okay, so the sigma algebra generated by this family will be a sigma algebra, and this sigma algebra we call the Borel sigma algebra. Okay, so the Borel sigma algebra, okay, this is a new definition. Okay, so the Borel sigma algebra, okay, will be a sigma algebra generated by this family. Okay, so generated by open intervals. Okay, so this is a sigma algebra. Okay, so sigma algebra generated by this family. Okay, so generated by open intervals. Okay. All right. So this is what this Borel sigma algebra is. So the Borel sigma algebra is a sigma algebra, it's a smaller sigma algebra, which is generated by extremes, okay? And theorem 2.21 provides actually a possibility for that, so that sigma algebra can exist. Okay, that was actually the basis. Now, I call it, okay, so this will be a second remark here, okay? Because that's quite interesting, you know, the formula. So it's I call it capital B, so capital B will be a Borel sigma algebra, okay? Over the set of real numbers, okay? And what you can find, I mean, you remember that the cardinality of the set of real numbers, okay, is equal to, or was equal to LF1. And remember what LF1 was. LF1 was actually the 2 to the power of LF0, and LF0 was, on the other hand, the cardinality of the set of real numbers. Okay, so this was actually the cardinality of the set of real numbers. And one interesting thing is that the cardinality of the Borel set, okay, so the Borel sigma algebra, okay, the Borel sigma algebra has exactly the same cardinality, okay. So this means that there is a bijection between the set of real numbers and a set of, you know, set of intervals, let's say, a set of the Borel sigma algebra, which is generated by open intervals on a set of real numbers, okay. So let's say there are just as many real numbers, to put it short, okay, so to put it simple, just as many real numbers as intervals on the set of real numbers. This is very interesting, okay, but I'm not going to elaborate that because the proof is quite complicated to show this. Okay, so the cardinality of the Borel sigma-additivity is not larger than the cardinality actually of the set of real numbers, okay? Although, basically, I mean, this is a family over the set of real numbers, so the real numbers itself are in there, and also the empty set, so that is actually a strange result, but this is it, this is how it is, okay? We're not going to elaborate on that, but I will come back to it later because I will need that result, okay? So this proof here is quite complicated, so I don't want to bother with that, okay? But just, this is something that I ask you, I ask you to trust me here on this, okay? If you can or you cannot, it depends, all right? But this is true. Anyway, okay? So there are sets. You see that. So for instance, of course, the cardinality of the power set of the real numbers. This was the notation, right, for the power set of the numbers. Is going to be 2 to the power of L of 1, which is strictly greater than L of 1. Okay. So that means that there exists intervals, or that's not intervals. There exist sets, okay, subsets of the set of real numbers that cannot be written in terms of intervals. Okay, all right. You understand this statement, okay? So, but basically, this is something that you cannot yet imagine. These are very abstract sets. For instance, the Vittula set. Okay, I'll give you this example. So we'll talk about the Vittula set later. Okay, so that means that there exists, okay, so this means that there are subsets of the set of real numbers that are no Borel sets, okay? Okay, a Borel set is an element of the Borel-algebra, okay? So this is something that I didn't tell you. So the Borel set is an element of the Borel sigma-additivity, okay? So since the cardinality of the power set of the set of real numbers is strictly greater than that of the Borel-algebra, this implies that there exist some sets, subsets of the set of real numbers which are not Borel sets, okay? Which are not actually elements of the Borel-algebra. This must be the case, and one example, the famous example, will be the so-called Finitely set, okay? So just, I'm adding here, this is an example. We're going to look at that, so this will be the Finitely set. Okay? The Finitely set is a subset of the set of real numbers which is not, or which cannot be written in terms of intervals. Okay, you're going to find out what it is later. It's a kind of wide abstract, this is how it is. Anyway, okay? But no, we're not talking about that now. Now, okay, so let's continue here. And what you can ask to conclude here, because the family of, this sigma-additivity, the Borel sigma-additivity is closed under complementation. That means that the closed intervals must be also in there, right? Okay, so this sigma-additivity actually consists of open intervals in a set of real numbers, and the complements of actually open intervals are, okay, so closed sets are those which complements are open, so that means that the complements of these open intervals must be also in there, which means that there has to be, at least one closed interval which is also a Borel set, right? So this means that and this implies, on the other hand, that the family or the sigma-algebra generated by closed intervals, okay, will be also a Borel sigma-algebra. Okay, so this is a lemma here, actually. Okay, so that is the same thing, which states that what is true for here for open sets is also true for closed sets. Okay, so the same Borel algebra can be generated by means of a family that has closed intervals. Okay, so a sigma algebra, okay, sigma algebra generated by a family of closed intervals on, okay, or closed sets to be precise, on the set of real numbers is also a Borel-algebra. Okay. All right, but this is just something that applies, and this follows directly, actually, from the property of closure under complementation of the Borel-algebra. Okay, so since the Borel-algebra is the closure under complementation, which closed intervals must be also in there, so actually this Borel-algebra can be generated by closed intervals as well. Okay. Now that is what the statement is about. Okay, this is due to the closure under complementation of the Borel sigma-algebra. Okay, guys. Now we introduce a very important concept, namely, we're talking about measures, but first we do that, so we can actually assign certain functions. Okay, for instance, we can define certain functions on sigma algebras. Okay, so the function what we have here is, okay, so this is going to be a new definition. Okay, so this is going to be the next definition. This corresponds to definition 3.12. Okay, so a function. So we have, let's say, so A, capital A is that, so this is a sigma algebra over omega, and the function, I call the function u. Okay, you all know what a function is, we define this. So the function u, which is defined on the sets of the sigma algebra, and that maps the sets of sigma algebra to the set of real numbers, okay, is said to be the first thing is pairwisely additive. Okay, so pairwisely additive. Okay, if, maybe remember this, if actually the image of a union of two sets is equal to the sum of the images. Okay, so if the image of the union of the two sets equals the sum of the images, maybe you remember that from probability theory, right? So I will try to, later on, I will try to define what a probability measure is, but we do this step by step. Okay, so first I have to tell you what the measure is, and for that we need to know what a pairwisely additive function on this sigma algebra is. Okay, so in case that if the sets are pairwise and disjoint, so if A and B, okay, so if the intersection of the two sets are empty. Okay? Okay, so if that's true actually for all, okay, so for all sets from the sigma algebra. Okay? Later I'm going to give you examples so you see what a pairwise additive function is. Okay? And we have the next definition is a so-called finitely additive function. Okay, so a function is called finitely. Okay? If, let's say, the image of a finite union, okay, of pairwisely disjoint sets, okay, so here you have n, and so n is a finite number, guys, you see? Okay, so that's why I'm putting more emphasis on it. Okay, so n is a natural number which is actually finite here. So the image of a finite union is equal to the sum of the images, okay? So we have a finite sum, okay, so I goes from 1 till n, of course, okay, so n is finite. Alright. So the image of the finite union of these pairwise and disjoint sets is actually equal to the sum of the images. Okay, so if, let's say, if the sets A1, A2, etc., AN are pairwise and disjoint, what does it mean? Pairwise and disjoint. Okay, so if you just take 2 and then the intersection of the 2, then what you get is the empty set. Okay, so the intersection of any 2 of these sets will be empty. Okay, so that means, i.e., the intersection. Okay, so AI and AJ is empty, provided that actually I is not equal to J. Okay, and that must be true for all. Okay, so for all elements. Okay, so these sets are actually all elements of the sigma algebra in which the function is defined. Okay, so this is what finitely, this is what a finitely additive function is. So this is finite additivity, if you say like that. Okay, now finite additivity and pairwise additivity is equivalent due to actually the associativity property of the union and the associativity property of the addition. Okay, so these two things are equivalent, but I will summarize it later. Okay, so before we summarize that, we're going to give you an example, so maybe you don't understand this concept, so I will come back to it. Okay, so, and the last thing that I would like to define here is the so-called sigma-additivity or countably additivity, or countably additive or sigma additive. Okay, so these two things are equal. Okay, if the statement, the additivity property, is also true for a countable union, not just a finite union. Okay, so the countable union is, okay, so you have that the image of a countable union. Okay, so I goes here from 1 to plus infinity, guys. Okay, that's the difference. Okay, so this is not actually the same as finite unions. I've seen this before, right? Okay, so for instance, the finite union of open and closed intervals. So for finite union of closed intervals can be also open. Okay, so you know that this is something that finite additivity does not imply countably additivity and vice versa. So therefore we have to define this new concept here. So the image of a finite union of these pairwise and disjoint sets must be equal to the countable, the image of the countable union of these pairwise and disjoint sets must be equal to the countable sum, okay, of the images. Oh, sorry, I forgot the sets here. Okay, so these are the sets. Okay, so the image actually of the countable union of these sets is equal to the countable sum of the images of these sets. Okay, so this is what it means. Okay, so, and these sets are pairwise and disjoint. Okay, so for the pairwise and disjoint sets, disjoint sets A1, A2, which are from the sigma algebra. I don't have space for the new side here, guys, so, but this is actually the same thing too. These sets are pairwise and disjoint still, okay, and all of them are elements of the sigma algebra. Okay, now let me give you an example, so maybe you don't understand this concept, so what that means, okay? Because this sounds a little bit, this sounds actually much more complicated than it really is, okay? All right, can I continue? Okay, you got that? Okay, I shall wait, everybody? Okay, good. I have to open a new slide, so basically, okay, let's consider an example, and this will be example number 8. Okay. Okay, so this will be part of example 8. Okay. Okay, so then you understand what a countable function is. So suppose that omega consists of the elements A, B, and C. It could be some natural numbers or what you like, anything you like. And you have capital A, and capital A is as follows. You have sigma, you have the empty set, then you have the set, the elementary set that has A as its element, and then you have the set that has B and C as its element, and omega, okay? And of course here you can find, I mean this is not difficult to show that A is a sigma algebra, okay? That is quite obvious. Why is that? Because it's closed under complementation, and it's also closed under countable unions. Now, since omega is finite, it's actually enough that for the set to be closed under finite unions, okay? Because omega is finite. Okay, so if omega is finite, then it's actually enough for a sigma algebra to be closed under finite unions. All right? But that statement is actually true. Okay? Now we define a function on a function mu, okay, on the sigma algebra as follows. Okay, so here, for instance, I mean, what you do is actually you have the function and you put the elements of the sigma algebra in it. Okay, so then you get certain numbers. So for instance, for the image of the empty set should be actually 0. Okay, it could be also something else, but it's not important. The image of the set, so this is the set here of the set that has A as its element, shall be equal to 0.5, and the image, let's say, of this element here. So we talk about B and C. Okay, shall be equal to 0.6, and the image of omega shall be equal to 1. Okay, so this is a function, obviously. Okay. Right? Is this function bijective? Question mark? What do you say? Is this injective? Two different arguments always have two different images. Is that true? Right? Yeah, it's true. Okay. And what about surjectivity, guys? Is there always a pre-image for any element? No? You say no? Why not? Which element does not have a pre-image?
Every element greater than 1 of.
Yeah, so for instance, what about the element 2, right? So the element 2 does not have a pre-image, okay? So it's not surjective, right? Okay? Okay, so it's injective, but it's not surjective, right? So then the function is not what? Bijective, all right, okay. But it doesn't have to be, so who cares, right? Sure, that was just a question. We just repeat these concepts, okay? So that could help you for the assignments. So, okay? Good. Now, so this function is injective, but not surjective. But anyway, but this is not what we're talking about. Now, the problem is here that this function is not sigma-additive. Okay, so then we show that this is not sigma-additive. Why is that? Okay, so what is, for instance, I mean, look, check it out. So for instance, what would be, I mean, you can see this here clearly. So what would be the image of a union, let's say the union of A and B and C? Okay, now first off, what is the union of A and B and C? Okay, so what is that? What do we get if I unify these two sets, guys? What do we have? What do we have? Excuse me? Okay, maybe you see this over here. Okay, so the union of A and B and C is what? Is? Okay, okay, so maybe you don't see this, guys. Don't be afraid, okay? Okay? There is no such thing as participating, you know, during lecture, okay? So I will not give you grades for that, okay? So just like in school and stuff, okay? So this is actually the set that has A, B, and C in its element, and this is actually omega, right? Okay, and what is the image of omega? The image of omega is equal to 1, okay? All right, get that? Okay, so this is the union. You understand? But what about, I mean, these sets are disjoint, right? So, of course, this is something that we should add here, but these sets are disjoint. So what about the sum of these two images, okay, from these sets? Okay, so what about the sum? Okay, so what about the image of that plus the image of that? Second one. What's the image of the first one? The image of the first one is?
0.5.
Yes, 0.5. And the image of the second one is? 0.6. And this is not equal to? This is equal to 1.1, right? But it's not equal to 1, right? Okay, so this is what we got here. Okay, so that's the first one. Okay, and here you have the second one, guys. Okay, and the sum of the two is not equal to the image of the union of the two sets. Okay? So therefore, then what? Then the function is not, what? Okay, so then the function u, okay, so then u is not sigma additive. Okay, so it's not additive actually. Okay, it's not sigma additive here. Okay, got it? Okay, because the union of, or the image of the union of pairwise disjoint sets is not always equal to the sum of the images of these pairwise disjoint sets. You understand? Okay, so here the image of the union is not equal to the sum of the images. Got it? Okay, so of course these two sets are pairwise disjoint, so the intersection of A and B and C, okay, is of course empty, right? So this is of course empty. If that was not the case, then the function would not have to be actually additive on that. All right, got it? You're looking kind of confused, guys. To be honest, is this really something that bothers you? Okay. Are there any problems regarding this? You can be honest, no, right?
Why is it sigma additive and why is it not sigma additive, but it is pairwise additive?
It is pairwise additive. It's not pairwise additive either. Okay, so if a function, let me just give this remark. So if a function is sigma additive, okay, so sigma additivity always implies, okay, always implies finite additivity. Okay, and finite additivity, on the other hand, is equivalent to pairwise additivity. Okay, so guys, I mean, look, I'm not talking about the implication that this is equivalent. So that's actually how it is. Okay, so this statement is equivalent to this one. All right. Why is that? Just think of actually what kind of properties do we have. Okay, so for instance, let's say a function is, let's say the function is pairwise additive, and what you can see here, for instance, is that you have the image of the union of A, B, and C. Okay, so if you want to know that is also also additive actually for, let's say, the union of three pairwise disjoint sets. Okay, so what you can do here is that you can generate just actually two of them, right? So if you have a finite union of sets, then you can actually use the associativity property of a union. You can get actually two of them, right? Okay, and if the function is pairwise additive, all right, so then this will be equal to the union of A and B plus the image of the set C. Okay, so the image of the union and the image of the set C. And now if the function is really pairwise additive, then the image of the union here will be equal to the sum of the images. Okay, so pairwise additivity implies finite additivity due to the complete induction. Remember that method, complete induction? Okay, that was a proof method. Maybe you consider that. Did you consider that in mathematics? Okay, so due to complete induction, this is also an implication which is here equivalent, because if a function is pairwise additive, then it must be also finite additive, and if it's finite additive, then it must be pairwise additive. So this is actually equivalent, but it's not going to be sigma additive. Okay, all right. But it's, let's say if it's not finitely additive, which is here the case, right? So this function is not finitely additive because it's not pairwise additive, so it's not pairwise additive, it cannot be finite additive. And finite additivity is necessary for sigma additivity, guys, all right? But it's not sufficient, so if that statement is not true, then what about this one? Then this statement cannot be true either, so sigma additivity cannot be true either. You understand? Okay? All right, so that's why I introduced you to propositional calculus. Okay, so finite additivity is necessary but not sufficient for sigma additivity. So if a function is not finitely additive, then it cannot be sigma additive. Okay, but if it's sigma additive, then it's always finitely additive. Always. All right. Okay. You understand? Okay. Good. Now. Okay, so that's why, I mean, this statement is not a direct, I mean, you can, actually you would also conclude here that the function is not pairwise additive, and this is equivalent for the function not being finite additive, and then after that the function is, of course, and this implies that the function is not sigma additive either. Okay, so that statement here that I made here, this is that statement here, I'm talking about this one, okay, is true, okay, because the function is not finite additive, okay, which implies on the other hand that it's not sigma additive. Okay, guys? All right, so this is actually part of example A, right? Now, this is something that we actually said here. Now I would like to make another statement here, and this is very interesting also, okay? So, remark, okay? So, and this is, I would like to show that. So, if a countable additive function has a finite image, so suppose that a function is countable additive, okay? So suppose that the function u is sigma additive or countable additive, as you like. Okay? Then if at least, okay, one image, okay, so sorry, no, if at least, or let's say, no, sorry, if there is, okay, so if there is at least one set, and I call it the set E, okay, which is an element of the sigma algebra that has a finite image, okay. What does it mean? A finite image means that the image of this set, okay, regarding this function is strictly less than plus infinity, okay, so or this is actually a notation for that, then the image of the empty set, the image of the empty set is 0. Okay, so that means that the image of the empty set will be 0. Okay. On the other hand, the contrary is not true. So just because the image of the empty set is 0, it doesn't imply that there is at least one image from this algebra which has a finite. There is one set from this algebra that has a finite image. Okay, so this is not true. On the other hand, but if there is at least one set which has a finite image, then the image of the empty set will be 0. Okay, I would prove this right now. Okay.
Okay, my question is how does this concept of additivity, which we have here,
yeah,
the sets and pairwise and sigma algebras, relate to the usual concept of additivity in the real space, for example, with functions?
What is additivity of functions here?
Yeah, basically you can take as an argument the sum of two real numbers maybe,
yeah,
and you put this into a function, and you can kind of check if this is the same if you put the
so the image of the sum will be the sum of the images,
yeah.
right? Okay, I understand. So, well, it could be. It's actually quite similar, right?
Yeah.
So it's not a big. I mean, this is just only true for linear functions. So linear functions are additive.
Is this
and
a generalization of this concept?
Not really, because we define a function on a different set. Okay, so you're talking about functions of real numbers, real valued functions of real numbers actually. Okay, these functions are also real valued functions, so we have actually real numbers as a result. But the difference is that it's not defined on a set of real numbers, it's defined actually on a sigma algebra in particular, and it could be something else. Okay, so that's, I mean, you can call it a generalization, but I think to my estimation, I'm not sure of this, but linear functions are additive, but I'm not sure if all functions which are additive are linear. Okay, but I think that this is a property that they have. For instance, integrals are also additive. Okay, the sum of the integrals is equal to the integral of the sum, right? or for instance, the differentiation. Okay, so the derivative of a sum equals the sum of the derivatives. So that property is also true for other concepts, not just actually functions which are additive themselves, but for instance, if you define, for instance, the differentiation. Okay, so the differentiation, you actually use sign for each function its derivative, right? So and that function is also additive, maybe. Okay, so that could be actually the case. So this means that the derivative of the sum is equal to the sum of the derivative. Now the problem is that the addition and the union, okay, are not equivalent. Okay, but they're both associative and both commutative, but the union is also idempotent. Okay, idempotency means, remember that what it was? So idempotency means that the union of two sets where actually both sets are equal is actually the set itself. Okay, so and that is not true for actually for yes. So for addition, right? So a plus a is not equal to a. So the addition is not idempotent. Okay. Now and here you also have to have that the sets of which the union is actually consists of, okay, for additivity of a function must be disjoint, or let's say pairwise disjoint to be precise. Okay. So there is an analogy between the two concepts, okay, but it's not completely equivalent. Okay. Good. Now, why is that statement true? So let's say that you have a finite image. I mean, what you can actually conclude here is that, let's say you have, okay, so I will show the statement right now. So why this is, okay, so this is actually because, I mean, the image of this set is equal to, you can see this here, the image of the union of the empty set and E, because the function is sigma-additive, okay, so if the function is sigma-additive, and you can see this here, right, then this will be equal to that, right? That's quite obvious, all right? And this is also true for a countable union. So if you have, like, for instance, the union, okay, so of empty sets here, countable times, okay, and then the set E, all right? Now, since the function is sigma-additive, we get here that this will be equal to the image of the countable union of these empty sets here, okay? So you have the empty sets countable times plus the image of the set E, okay? And this is only finite, okay? So you can see this here. This is only finite, right? If the image of the empty set is 0, okay? So this is only finite because, I mean, I make another statement here so you can see that here clearly. So this will be the sum, the countable sum of I is equal to 1 to the plus infinity of the empty set, okay? Of the image of the empty set plus the image of E. Okay? Now this is only finite. The sum is only finite if the image of the empty set is equal to 0. So if the image of the empty set is not equal to 0, then this sum will not be finite, right? And you can see that clearly that this thing is equal to that one, you see? So the image of E is equal to the image of E plus the image, the sum of the images of these countable empty sets, right? Okay, so this you have a countable sum. So, and if, let's say you have the sum of equal elements, now if the sum is actually countable, okay, so you have a countable sum, or countable sums, let's say, then the sum can only be finite if the numbers of which the sum consists of is actually are all 0, right? So if the numbers are equal, right? Okay, so if, I mean, the sum can converge to 0 if, you know, you have different sum ends, but if the sum ends are equal because they must be equal, then they actually must be all equal to 0 if you want to make sure that the sum is finite. Okay, so that's actually what the proof is about. Okay, so if there is at least one set of which the image of the set is finite, then of course then the image of the empty set must be 0, otherwise it wouldn't work. All right. But on the other hand, just because the image of the empty set is equal to 0, it does not mean that there exists, a set from the sigma algebra of which the image of the set is going to be finite. You understand that? Okay? Alright? So the sum is only finite if actually the image of the empty set is equal to 0. So therefore, if this is finite, then so this will be the statement. So finally, and let me just summarize that. Okay, so finite, so finally, so if the image of this set is finite, then this implies that the image of the empty set must be equal to 0. Okay? All right? Got this? Okay. Now, and let me define what the measure is. Okay, so because we were talking about this concept in later, because I need that. Okay, so and this is a non-negative sigma-additive and sigma-additive function, I call it mu, on a sigma algebra, so defined on a sigma algebra, where actually I call it this A, so A is a sigma algebra over the set omega is called measure. Okay, this is the concept that I'm defining here. So non-negative and sigma-additive functions over on the sigma algebra over a set omega is called measure. Okay, so this is what I define here. If the image of the empty set is equal to 0, that's it. Okay, so if the image of the empty set of the function is equal to 0, then the function is called measure. Now this will be the case, okay, so provided that the function is sigma-additive and non-negative. Now this can be generalized also for functions that are also negative, okay? So for instance, you mean like, you know, the temperature, right? The temperature in Celsius is measured, you know, in the regular case. So temperature can be negative, right, in this case. Okay, but we don't have anything like that. So we just have actually positive values here. Okay, so because if I mean, there is a possibility to define that also for functions that can be negative as well. But if I add this concept here, then you know the other concept that we follow will be too much complicated. Okay, so we don't care about this at that time. So we only define actually images, or we get only images that are non-negative. So either 0 or positive. Okay, so this is just for practical reasons, guys. Okay, so of course, for instance, temperature, as you consider, like for instance, Celsius can be negative. Okay, so as an example, under this definition, this will not constitute a measure, but just for your information, I do this just for practical reasons to make it simple. Okay. So if the image of the empty set is equal to 0 of a sigma-additive function, then the function is called measure. That's it. And that can be ensured just by one set, namely if one set has a finite image, then the function will be automatically measured. Okay, so if one image of a sigma-additive function has a finite image, okay, so if the set from the sigma algebra has at least one set has a finite image of a countable additive function, then it's automatically measured because the empty set has a 0 image. Okay, this is what a measure is. Okay, now the sets here, and this is the next definition. The sets, okay, so the sets, then the sets from the sigma algebra. Okay, so I call them A1. Okay, so A1, A2, etc., 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 which are all elements of the sigma algebra, are called measurable sets. Okay, these are the measurable sets, or you can call them A measurable. That is also another concept. Okay. Then what you have here, if you just continue, I mean, this is what I do. Okay, so the sets, I mean, you can assign actually measures, let's say, to these sets because the function is sigma-additive, okay? And the image of the empty set is 0, so actually what you have is that these sets defined in the sigma-additivity, okay, which are element of the sigma-additivity, always have an image, and we call these images actually measures itself. Okay, so then we call these sets measurable sets. Okay. Now, and we continue. So here, the ordered pair that consists of omega and the sigma-additivity, this will be a measurable space. And the ordered pair, okay, and the ordered triple, sorry. So you have a triple here consisting of omega, the sigma-additivity, and the measure u, okay. I need a little bit more space, you guys, so that was not long. I just, I had to open the side of I keep that here, okay. So I want to push that a little bit further to the top, okay, so that I have more space, okay. Okay, oh. So take that too, okay. So this is a measurable space, okay, so this is how it's defined. This is just the ordered pair, okay. So the ordered pair consisting of omega and the sigma-additivity is called measurable space because that offers you, let's say, the possibility to find a sigma-additive function for which the image of the episet is 0. And the triple, okay, consisting of omega, the sigma-additivity, and the measure is called measure space. So sometimes in the literature, these two things, measurable space and measure space, are used synonymously. Okay, I don't know why. Okay, people mess it up or whatever. Okay, so distinction is not really that important. Okay, but you should actually know the difference. Okay, so for measure space, you have also the function which is explicitly defined. Okay, and for a measurable space, that just offers you to define actually a measure on that space. Okay, this is it. Okay, so that's it. So if the function is not explicitly given, then you call the ordered pair omega and a sigma-additivity a measurable space. And if you have an explicitly defined measure on that measurable space, then you could call the ordered triple consisting of omega, the sigma-additivity, and the measure itself. You call that the measure space. Okay, that's okay. But this is just technically, so that's what I would like you to actually consider. Okay. We'll talk about probabilities later, so you're supposed to know by then what probabilities are, especially what a probability space is, and using that, I will define what a probability will be. Okay, so I do this step by step. So then, first we define sigma-additive functions, then we define measures, then we define measure spaces, and then I will also define probabilities and probability spaces as well. Okay, so that's what you see next. Okay, but see what kind of properties these functions have apart from being sigma-additive. Okay, so we summarize the properties of these functions. Okay, and now the first property is that I'm going to put this in the remark.